Many datasets in the real world are complex, and they often contain a large number of features or variables. This is what we call high-dimensional data. For instance, a customer dataset might have hundreds of columns. These columns could track every purchase click and interaction. A medical dataset might have thousands of genetic markers for each patient. Working with so many features presents a significant challenge. It makes it difficult to visualize the data's underlying structure. It also slows down our machine learning models. Principal Component Analysis, or PCA, is a cornerstone of dimensionality reduction. Its primary objective is to reduce the number of variables in a dataset. It does this while preserving as much of the original data's variance as possible. Variance is a measure of how spread out the data is. PCA identifies new, artificial axes called principal components. These components are ordered by the amount of variance they capture. The first principal component is the direction in the data along which the points are most spread out. The second principal component is the next most important direction. It must be orthogonal, perpendicular to the first. The intuition behind PCA is straightforward. It seeks to find a new coordinate system for your data. In this new system, the most important information is aligned with the first few axes. Imagine a flat, oval-shaped cloud of data points in a three-dimensional space. PCA would identify the longest axis of the oval as the first principal component. This single direction captures most of the variation in the data. To understand how PCA finds these principal components, we need to touch upon some mathematical concepts, but we will do so without getting lost in complex formulas. The process begins with the covariance matrix of the data. The covariance matrix is a square table. It describes how each pair of features in the dataset varies together. A positive value means that as one feature increases, the other tends to increase as well. A negative value means they move in opposite directions. This matrix summarizes the linear relationships and the spread of all features in the dataset. It is the raw material from which PCA extracts its insights. The principal components are, in fact, the eigenvectors of this covariance matrix. An eigenvector of a matrix is a special non-zero vector. When the matrix is multiplied by this vector, the result is simply the same vector scaled by a number. This number is called the eigenvalue. For the covariance matrix, the eigenvectors point in the directions of maximum variance in the data. The corresponding eigenvalue tells us exactly how much variance is captured along that eigenvector's direction. Therefore, the eigenvector with the largest eigenvalue is the first principal component. To make these ideas concrete, let us walk through a practical demonstration. We will use the classic iris flower dataset. It contains 150 samples: setosa, versicolor, virginica. For each sample, there are 4 features measured in centimeters: sepal length, sepal width, petal length, petal width. Our goal is to use PCA to reduce these 4 dimensions down to 2. The first step in our workflow is to load and prepare the data. It is a critical best practice to standardize the features before applying PCA. Standardization involves rescaling the features so that they have a mean of 0 and a standard deviation of 1. This is important because PCA is sensitive to the scale of the features. By standardizing, we ensure that each feature contributes equally to the analysis. Next, we will instantiate and fit the PCA model from Scikit-learn, setting NT components to 2. We then project our 4-dimensional data onto these 2 principal components. We will create a 2-dimensional scatter plot using the 2 new principal components as our axes. Each point represents a flower, colored by species. Typically, the setosa species forms a very tight and separate cluster. Versicolor, virginica. This confirms the first 2 components capture enough information to distinguish the flower types. Now, let us shift our focus to a very different technique, t-SNE. The name stands for T-Distributed Stochastic Neighbor Embedding. Unlike PCA, t-SNE is a non-linear dimensionality reduction method. Its primary goal is visualization, specifically revealing underlying structure at different scales. It is particularly effective at creating compelling two-dimensional maps of high-dimensional data and three-dimensional maps of high-dimensional data. The core idea of t-SNE is to place similar data points close to each other in the low-dimensional map. It models neighbor probabilities in high dimensions and recreates them in low dimensions, preserving local structure. Imagine a tangled ball of yarn. PCA might flatten the ball and distort the weaves. t-SNE tries to carefully unroll it, placing same color strands together. Perplexity relates to the number of close neighbors each point considers. Small perplexity, like 5, focuses on tight local groups. Larger, like 50, reveals broader structure. t-SNE iteratively adjusts positions. Similar points attract, dissimilar points gently repel, evolving from random scatter into tight, well-defined clusters. Note it does not preserve global distances. Global arrangement can be misleading. Focus on local neighborhoods. Section 6. A practical t-SNE demo. Clustering the MNIST digits. To see t-SNE in action, we will use the MNIST database of handwritten digits. The MNIST dataset consists of 70,000 small, grayscale images. Digit 0, Digit 1, Digit 2, Digit 3, Digit 4, Digit 5, Digit 6, Digit 7, Digit 8, Digit 9. Each image is 28 by 28 pixels. We flatten each image into a single vector. Vector length, 784 features. Our goal is to reduce these 784 dimensions down to 2 to see if the plot forms 10 distinct clusters, 1 for each digit. Our workflow differs because t-SNE is computationally expensive. We will use a random subset, perhaps 2,000 to 5,000 samples. We load this subset and scale pixels from 0 to 255 down to 0 to 1. A common strategy is PCA pre-processing, reduced to 50 dimensions to speed up t-SNE and denoise the data. Then run t-SNE with n components equals 2, perplexity around 30, for roughly 1,000 iterations. We plot the coordinates, coloring points by their digit labels. The expected result is a stunning visualization with 10 distinct clusters that gives us a very intuitive view of the data. Section 7. Code in action. Scikit-learn for PCA and t-SNE. Implementing PCA and t-SNE in Python is remarkably straightforward, thanks to the Scikit-learn library. For Iris, load data, scale with standard scaler, create PCA with n components equals 2. xduck PCA equals PCA.fits, transform of xsucks scaled. Plot xsucks PCA with species labels for color. Optionally, use a scree plot to see explained variance. For MNIST, scale pixels, PCA to 50. t-SNE with n components equals 2. Perplexity equals 30. Random state equals 42. t-SNE equals t-SNE.fit transform of x PCA. Note that t-SNE only has a fit transform method, not separate fit and transform, because the mapping is data specific. Be mindful of runtime. PCA is fast. t-SNE can be slow. A few thousand MNIST samples might take a minute or two on a standard laptop. So, plan accordingly when you run these experiments. Section 8. PCA versus t-SNE. Choosing the right tool for the job. Now that we have explored both PCA and t-SNE, the crucial question is, when should you use one over the other? The choice depends entirely on your goal. They are not interchangeable tools. They answer different questions about your data. PCA is a linear technique. It preserves global structure and overall variance. It is deterministic and reliable for pre-processing and compression. t-SNE is non-linear and great for visualizing clusters and local structure, but it does not preserve global geometry. Intercluster distances can be misleading. PCA is efficient even at scale. t-SNE is intensive with runtime growing quadratically. Use PCA first to reduce to about 50, then t-SNE for detail. Use PCA for fast, linear dimensionality reduction, compression, and noise reduction. Use t-SNE when your primary goal is visualization of clusters, and avoid over-interpreting global layout. Final thoughts and best practices. In conclusion, Dimensionality reduction lets us peer into complex datasets and extract meaningful patterns. Always scale before PCA. For very high dimensions, use PCA before t-SNE. Experiment with perplexity and set a fixed random state for reproducibility. Seeing patterns emerge with just a few lines of code is powerful. So, start exploring your data today.